March 2018, Portugal produced enough renewable energy to power the whole country for a full month. And this is the only reason why that was possible. Wind turbines are leading the transition away from fossil fuels, and this well-known three-bladed design has proven more reliable and efficient than any other. But if you think design improvements are over, you might want to think again, because 2019 is heading to become the year of change, with new creative solutions in the market. Is there gonna be one revolutionary wind turbine? Whatever it takes, our team will find it out. Because one thing is for sure, the wind will keep blowing. With no time to lose, we knew exactly what we wanted from the beginning. A horizontal axis wind turbine which will rotate clockwise as seen from the wind direction. Its power coefficient should be maximized at a selected tip-speed ratio between 3 and 8, and its maximum angular velocity should not exceed 3,000 rotations per minute. The biggest challenge, however, was its limited size of 400 times 100 times 150 millimeters. Besides, it should be lighter than 200 grams and 3D printed as a single part.
A wind turbine extracts mechanical energy from the kinetic energy of the wind. This disc, which represents a wind turbine, generates lift and also slows down the V-node due to the pressure drop behind it. If we consider the momentum balance and these equations, combining these two, we get average velocity, and hence substituting back in, we get the power. When we differentiate this equation, we get that the velocity ratio behind relative to the velocity ratio in the front is equal to 1/3, and if we substitute that in the power equations, we get that the maximum power coefficient that we can generate is equal to 59.2%, which is known as the Betz limit. But in reality, due to weight losses and friction, there can be more than 35% of CP max. These equations are valid if the induction factor is less than 0.4%, but we considered and fixed that when the case was more than 0.4. In a normal airfoil, the lift is generated upwards. If the airfoil was kept like that, the wind turbine would rotate anti-clockwise instead of clockwise. Hence, we had to reverse that upside down to determine the spinning directions we would like.
More wind turbine blades give maximum power and efficiency. However, many blades closely spaced may introduce turbulent regions of air and mixing when rotating at high speeds. After a three-bladed design, the efficiency doesn't increase that much. For our application, due to the mass constraint and to minimize the blockage effect, we decided to go for a two-bladed design.
So the chord and pitch angles were calculated using the Smith distribution. As you can see here, the relative velocity changes as the radius of the blade changes and its maximum near the tip. Thus, we had to introduce a twist angle, except for the pitch angle that's introduced already. So the Prandtl's tip loss factor corrects our calculations for the wake turbulence that it's being generated behind the wind turbine. So we added also this in our boundary element momentum theory code, and we also introduced the Glauert corrections, which concerns for a induction factor smaller than 0.4. And using these and the definition of lift and drag, we concluded on the axial induction factors.
Now that we have optimized the blade aerodynamically, we need to make sure that structurally it is able to withstand the loads that the blade will experience during testing. The two main loads we are concerned with are aerodynamic loads, which will cause the blade to bend in this direction, as well as centrifugal forces. As the blade spins, the forces act radially. First, we look at aerodynamic forces. From this diagram, we can see that the resultant force acting on the blade can be decomposed into a tangential force as well as a normal force. The tangential force is what causes the blade to spin, and what we are concerned with is the normal force, which causes bending stresses. To calculate these stresses, we simplify the problem by dividing the blade into 25 discretized sections, and assume that aerodynamic forces are discrete loads at each section. The second force we look at is centrifugal force. Again, we simplify the problem by discretizing the blade into 25 sections. The centrifugal force on each section is labelled dFc and is calculated with this formula. Then, to obtain the total centrifugal force acting on each section, we perform this integration. This force is then divided by the cross-sectional area to obtain the stress acting at each section. MATLAB was used to calculate and plot the resulting stress distribution across the entire blade, as shown. Notice that the stress is significantly higher at the root due to a reduction in cross-sectional area as the blade tapers down to be integrated to the hub. This is also why we have chosen SG6040, a thicker aerofoil, to be the aerofoil at the root, because it gives a larger cross-sectional area to reduce the stresses experienced. The sum of stresses from both sources resulted in a maximum stress occurring in the root, which is less than 60% of the critical stress and was thus assessed to be structurally sound.
Among the requirements, the CAD model had to fit in a small box corresponding to the 3D printer capabilities. This was a great challenge considering the longer the blades are, the better the performance is. Therefore, we decided to design what could be called a foldable wind turbine using a hinge mechanism. The hub plays a central role. It is divided into two parts, each one supporting one blade. The hinge has strategically been installed at the back. This presents the advantage of not disturbing the aerodynamics. A small amount of space was left in all three dimensions to ensure that both parts can fully move without being fully independent. This is called an offset hinge, and it is only after printing it that the blades have been assembled using glue.
Our nose cone was designed using the Hack series. The main consideration was to have minimal resistance to the wind flow, as the nose cone itself does not generate any power. To stay in line with the mass and structural requirements, we used the Von Karman series, which is a Hack series modification for minimum drag for given length and radius, which gave us the following nose cone curve. The top half of the nose cone was hollowed to a thickness of 2 mm to save weight, while the bottom, where the wing attachments were, was kept solid to maintain structural integrity.
The race for wind turbine efficiency brings about more elaborate and streamlined shapes almost every day. Designers take their cues from nature, imitating evolution in designs such as the blended wingtip. But to blindly copy from nature without understanding context isn't enough, which is why our team decided the best decision is that which has the data to back it up. We used the flow simulation toolbox in SOLIDWORKS to do just that, and to decide if the blended wingtip, a concept just as popular in modern aircraft as predatory birds, would work in our particular case. Here is a comparison of the two models, one with the bio-inspired feature and one without. It is clear the winglets not only reduce weight behind the blade, resulting in cleaner airflow, but also reduce the pressure differential at the tip and therefore drag. Finally, a cut plot of vorticity shows us the winglet-equipped blade generates far fewer wingtip vortices, allowing it to extract more energy from the oncoming airflow. We made cut plots of both averaging and local rotating regions to confirm these findings.
We compared our design values to the experimental data we obtained through wind tunnel tests to validate our design calculations. As expected, the maximum power is generated at 12 meters per second and has a value of 61.6 watt. Beyond the rotation speed at maximum power is the stall region with tip speed ratio lower than the optimal one, hence there is no more power increase. The experimental TSR strays from the design value by 10%, which is small enough to be accounted for by the blockage effect. The correspondence of the design and test data validates our aerodynamic design method and corrections used. The fact that our wind turbine had negligible deflections and didn't underwent any failure attests our structural design methods.
During our design, we avoided taking unnecessary risks and focused on preventing failure. Because of that, we would be more confident in a phase 2 of our design, where it would have been beneficial to test the effect of the wingtips in the overall performance. Apart from that, our project was a great success. Get our wind turbine now on amazon.co.uk.